Good evening. I believe it is 7:30, but I see people are a little bit slow in coming in. So we'll wait for just a couple of minutes. We have a lot of material to cover, so it will not be a long delay, but I'll wait a couple minutes, then start. Thank you. Okay, good evening again. We will get started. This is SK Ghosh. I would like to welcome all of you to our web seminar today that is part of the training and capacity building program under Project S9 of the Urban Resilience Program RAJUK-URP. We started on these seminars in mid-March and we will go through middle of July. Hopefully many of you have attended prior seminars. Today it is module S9 and the topic is anchoring to concrete. Today I have an announcement, but I think I will wait until about the middle of the seminar to make it, because not everybody has come in yet. And I would like the largest number of people to listen to the announcement. Anchoring to concrete was not part of ACI 318 until the 02 edition, relatively recent, although it has been a while. Anyway, 02, 05, between 2005 and 2008 edition of ACI 318, there were changes in the appendix, and the requirements that you find in BNBC 2020 in Appendix K, that's where the anchor design provisions are based on ACI 318-08 requirements. So you are looking at the original provisions after one set of refinements had been made. I decided to include this part of it. Anyway, let me go through this. So ACI 318-08 is the source for Appendix K, and ACI 318-08 was adopted by the 2009 International Building Code, IBC. And 2009 IBC in the concrete chapter, chapter 19, said where strength design is used or where load combinations include earthquake effects, the design strength of anchors shall be determined in accordance with section 1912, which was strength design of anchors. Back in those days, there was allowable stress design of anchors and strength design of anchors. And IBC was saying when you were doing strength design for your structure that included the anchors, or when the anchors were subjected to earthquake forces, you had to do strength design. Now, I wrote in blue letters, and whenever you see blue on the slides, it relates to BNBC 2020, that there is no allowable stress design of anchors in BNBC 2020. All you have is strength design of anchors in Appendix K, as in king. The other thing that I thought I should mention, 2009 IBC said the provisions of this section 1912 that we talked about, shall govern the strength design of anchors installed in concrete for purposes of transmitting structural loads from one connected element to the other. Headed bolts, headed studs, and hooked, which can be J or L bolts, excuse me, cast-in concrete, and expansional anchors and undercut anchors installed in hardened concrete shall be designed in accordance with Appendix D of ACI 318 as modified by Section 1908.1.9, etc. So the IBC was sending the user to Appendix D of ACI 318 where the anchor design provisions were. And the other thing is that IBC itself made a couple of modifications to Appendix D. Now, you don't have any of that. No comparable provision in BNBC 2020. There is nothing in the code itself that directs you to Appendix K for anchor design, except for something that Dr. Akib found for me, section 6.8.8.3. So Appendix K itself is in Part 2, Chapter 6 of BNBC. This section is also part of Part 2, Chapter 6, and it says, in precast construction, anchor bolts or suitable mechanical connectors shall be permitted for satisfying section such and such. Anchor bolts shall be designed in accordance with Appendix K. But this section, this section is only for precast concrete. For cast-in-place concrete, there is no section that directs you to Appendix K. But I suppose since Appendix K is the only thing in the code that enables you to do anchor design, you will do anchor design by Appendix K. Okay, the Appendix K covers or the scope includes cast-in-place anchors as well as post-installed mechanical anchors. Cast-in-place anchors can be, the left-hand picture is a headed bolt. This is a hooked bolt, can be L or J bolt, and this is a headed stud. The head is welded to the shaft. Okay, so here it is a bolt, here it is a welded connection between the head and the shaft. So this is a welded stud, this is a headed bolt. All of that is within the scope of the appendix. Then there are different kinds of mechanical anchors. And the important thing that I didn't point out, the effective embedment depth, which is a very important quantity, is from the surface of the concrete down to the head, okay, in each case. And here the effective embedment depth for mechanical anchors is shown. So the scope of Appendix K. Now I gave you the Appendix D number out of ACI 31808, and if you replace the D by K, you will have the Appendix K section number out of BNBC 2020. Anchors used to, so the scope includes anchors used to transmit tension, anchors used to transmit shear, or anchors that transfer both shear and tension at the same time. The safety, the load factors and the strength reduction factors that we use in Appendix K consider in-service conditions of the structure. Not so the appendix is not intended for use for short-term loading and for construction loads. This is very, very important. Okay, so construction loads are not included in the scope of Appendix K. Neither are short-term handling loads. Okay? If you have to install anchors to transmit construction loads, that you have to go beyond Appendix K to do that. That is not within the scope of Appendix K, not intended for short-term handling and construction loads. The appendix has provisions, as I mentioned, for cast-in-place anchors and also post-install mechanical anchors. Very importantly, excluded from the scope of the appendix are specialty inserts of various kinds, through bolts that go through the body of concrete, multiple anchors connected to a single plate at the embedded end of the anchors. This is a pretty popular item when many times when groups of anchors are not working out, people try this to enhance the capacity of the group. However, the problem is the concrete at the interface of the plate, the concrete just above the plate, is of poorer quality. We know that, but we do not have a handle on how much poorer the quality of that concrete is. So the writers of Appendix D of ACI 318 decided to stay away from it. Since we don't know, let us exclude it from the scope of Appendix D. So this is not to say that these things cannot be done, but you cannot design them by Appendix D or Appendix K. That's all we are saying. Adhesive and grouted anchors, very, very popular, not within the scope of ACI 31808 or Appendix K of BNBC 2020. The adhesive anchors have since come into ACI 318 Appendix D, which is now Chapter 17, starting with ACI 31814. So adhesive anchors are now within scope, but we are talking about 31808. So our scope, Appendix K of BNBC 2020, does not include adhesive anchors. Also excluded from scope are powder or pneumatically actuated nails or bolts. So quite a few things are outside of the scope of Appendix K. Appendix K is based on the so-called concrete capacity design method, which predicts the load capacity of an anchor or a group of anchors by using a basic equation for tension, another basic equation for shear. Each of those equations for tension or for shear is for a single anchor in cracked concrete. And so the basic equation is for a single anchor in cracked concrete. This single anchor capacity in cracked concrete is multiplied by factors that account for the number of anchors in a group, if you have a group of anchors rather than a single anchor, edge distance, spacing, eccentricity of load application, and possible absence of cracking. If you can show that your concrete on the surface level loads is going to remain uncracked, then you get a correction factor larger than 1. So once again, this is very, very important. Concrete capacity design method predicts the load capacity of an anchor or a group of anchors by using a basic equation for tension, a basic equation for shear. Each equation is for a single anchor in cracked concrete, which is multiplied by factors that account for the number of anchors, edge distance, spacing, eccentricity, and absence of cracking. Before the concrete capacity design method, we used to use intersecting cones. The idea was when an anchor subject to tension pulls out of the concrete, it typically takes a chunk of concrete with it. We postulated back then that the chunk of concrete that comes out with the anchor is in the shape of a cone and that the failure angle is 45 degrees. If you had a group of anchors, you had to deal with intersecting cones, which was a pain. Anybody who has done anchor design by the old method would readily agree with me that it was pretty painful. Concrete capacity design method has replaced the 45-degree failure cone with a truncated pyramid. So now the postulation is that when a group of anchors in tension comes out of the concrete, the chunk of concrete it takes with it is in the shape of a truncated pyramid, and that the failure angle is 35 degrees rather than 45 degrees. These are basic differences between the concrete capacity design method and the 45-degree failure cone method that we used to use. Okay. So a truncated pyramid and the failure angle is 35 rather than 45 degrees. The 35-degree angle is based on quite a bit of testing at the University of Stuttgart, where they tested anchors with varying parameters and varying effective depths under tension load, and you see the test results presented here. Okay, so the failure angle is definitely nowhere near 45 degrees. 35 degrees was felt to be a much better representation of the test results. So this is where the 35-degree failure angle came from. The scope of Appendix K does not include high cycle fatigue or impact loading. However, seismic load effects are very definitely included in scope. For seismic design category C and higher, we have specific requirements given in section K.3.3, which are very important requirements. Okay, so seismic is not only excluded from scope, seismic is very much included, and we have specific requirements that apply to seismic applications. So we design anchors for factor loads coming from elastic analysis of the structure under applied loads. Load combinations are in section 6.2.2 of BNBC 2020. The fee factors for anchor design that go with those load applications are given in section D.4.4, or in your case K.4.4. I most of the time I added a K before the D here. Obviously, I forgot to do that. Okay. Load combinations. So in ACI 318 Appendix D, there was a choice of using load combinations in Appendix C rather than load combinations in Chapter 9. Those are traditional ACI load combinations that we need not worry about. There was a set of fee factors to go with those other load combinations. None of that is in BNBC 2020. So your only choice is load combinations from section 6.2.2 and the fee factors to go with those load combinations that are in section D.4.4. Now the K.3.3 section that I mentioned, seismic applications, if you have an anchor that is part of a structure assigned to seismic design category C, D, E, or F, the requirements that apply to that anchor are anchors in plastic hinge zones of structural members are outside of the scope of Appendix K. So seismic application If you want to put an anchor bolt at the end of a beam, you want to put an anchor into the beam near its column support, that anchor is excluded because there will be plastic hinging at that beam end. Cracking itself is a big enough problem. When it is plastic hinging, meaning extensive cracking may be yielding of reinforcement, we know very little as to how our anchor may be affected. So ACI 318 has said this is outside of scope of Appendix D. That does not mean, again, that you cannot do it, but if you want to put an anchor in the plastic hinge region of a member, you are on your own. Appendix D or Appendix K does not help you. It is outside of scope. Okay? Then, very importantly, design strength associated with concrete failure. So when you have an anchor embedded in concrete and you pull on it or you subject it to shear, the anchor itself may fail, the steel may fail, or it may be a concrete failure. There are multiple concrete failure modes that we have to consider under Appendix K. If it is a concrete failure mode, the corresponding nominal strength has to be reduced not only by a phi factor, which is usual, but by an additional 0.75 factor. So in other words, we lose 25% of the strength of an anchor right off the bat because it is a seismic application, seismic design category C, D, E, or F. You don't have E or F in Bangladesh, so don't worry about it. In your case, it is C or D. Okay? So if you have an anchor that is part of a structure assigned to seismic design category C or D, the design strength of the anchor is reduced. The nominal strength of the anchor is reduced not only by a phi factor, by an additional factor of 0.75, just because the anchors are subject to seismic forces. Then, very importantly, concrete is assumed cracked unless you are able to demonstrate that concrete is going to remain uncracked under service level load. And that demonstration is not simple. Okay, so this is very important. Concrete is assumed cracked under seismic applications unless you are able to demonstrate otherwise. Now, if you have an anchor in a structure assigned to seismic design category C or D, these are important restrictions. You have three choices. You have to design your anchor such that it fails. The anchor itself fails. You have to design for steel failure. And the steel failure has to be ductile. And what that means, I'll come to in just a little bit. So if it is an anchor that is subject to seismic forces, design category C and above, you can only have steel failure, no concrete failure. And the steel failure has to be ductile. This is choice number one. Your second choice is you can design to have the attachment, which would be like the base plate, undergo ductile yielding at a load that does not exceed the minimum anchor design strength. So you have to design for your base plate to yield before the anchor attains its design strength. Third choice is Forget about ductility, ductile anchor failure designed for overstrength. You make your anchor so strong that you don't have to worry about the failure mode. Okay, so reduce design strength by an equivalent of phi equal to 0.4 rather than the usual 0.75 or something like that. Okay, so design overstrength anchors rather than ductile anchors. So those are your three choices: ductile anchor failure, failure in the attachment before the anchor gets to its design strength, or overstrength anchors where you reduce nominal strength by a phi factor of 0.4. Now, we talked about ductile anchor failure. What is a ductile steel element? What is a brittle steel element? These are defined in BNBC. In BNBC, it is chapter 6. Anyway, the definition is that, so when you pull on an anchor, just like you pull on a reinforcing bar in a tensile test, if the elongation, typically measured over a 6-inch gauge length, is less than 14%, or the reduction in area, so you pull on the anchor, there is eventually necking, as we call it, the area reduces before there is a rupture. The reduction in area, if the reduction in area is less than 30% or both, either the elongation is less than 14% or the reduction in area is less than 30% or both, then you have a brittle steel element. If the elongation is larger than or equal to 14% and the reduction in area is larger than or equal to 30%, you have a ductile steel element. A steel element meeting the requirements of ASTM A307, which are very common, shall be considered ductile. Okay, so the anchors we typically use are ductile, but there are brittle anchors as well. Attachment, the term that we used, the definition is structural assembly external to the surface of the concrete that transmits loads to or receives loads from the anchor. So base plate is a very good example of an attachment. The modification factor lambda for lightweight concrete comes from the main body of chapter 6, and the section number is given. Now, as in the design of any structural element, the design axial strength of the anchor has to be larger than or equal to the required axial strength, and the design shear strength of the anchor has to be larger than or equal to the required shear strength. Okay. Now, for an anchor subject to tension, we consider multiple failure modes, and the lowest of the strengths corresponding to the multiple failure modes is the nominal axial strength N sub n, which has to be reduced by a proper phi factor. Similarly, for an anchor subject to shear, we also consider multiple failure modes. Whichever failure modes gives us the lowest design strength is the failure mode that governs, and that lowest design strength still has to be larger than or equal to the required strength. Okay. And if an anchor is subject simultaneously to tension and shear, then the interaction between shear and tension has to be considered. Okay. From this point on, I will introduce a numerical example and introduce the code provisions as we work out the example. I think it makes a lot more sense that way. I think it becomes much, the requirements become much more understandable that way. Without numbers, these things are too abstract to to be absorbed. Okay, so we have a wide flange column on a base plate that is attached to the concrete foundation by 6 anchor bolts, 12 millimeter headed bolts, ASTM F1554 grade 250 anchors, which are fairly common. So that means the yield strength of the anchor is 250 MPa. The ultimate tensile strength is 400 MPa. F sub C prime 40. The embedment depth, effective embedment depth, 300 millimeters, and the thickness of the concrete foundation is 460 millimeters. Okay. The seismic design category is C. Concrete is assumed cracked at service loads. Okay, so 6 anchors, the spacing this way is 200, the spacing the other way is 150 millimeters. Edge distance here is 100, edge distance here is 100. Okay, the other two directions, this way and that way, we have plenty of concrete. Now this way, when we need an edge distance, we have taken it in the calculations as 500 millimeters. Okay, so we have plenty of concrete. 500 millimeters is something that we have used for calculation purposes. First, we consider this group of anchors subject to tension, which is applied at an eccentricity of 25 millimeters with respect to both the x-axis and the y-axis as seen in the picture, the centroidal axis. Okay, so 25 millimeter eccentricity both ways. The failure modes that Appendix K considers in tension: the steel itself failing, concrete breakout failure, pull-out failure, concrete side face blowout, which happens to headed anchors that are close to an edge, the cover. So side face blowout happens when we have headed anchors that are reasonably deep and are close to an edge. It can happen in those situations, side face blowout. So we have a group of anchors subject to tension that is eccentric with respect to both axes. First, we check for possible compression in any of the anchors in the group, because compression anchors have to be excluded. We include in our calculation only the tension anchors. Okay, so we are looking at the x eccentricity. We have an axial tension applied at an eccentricity of 25 millimeters. So that tension is equivalent to a tension along the centroidal axis plus a moment, which is equal to the tension multiplied by the eccentricity, which is the tension times 25 millimeters. Okay, the concentric load will be divided equally between the 6 anchors, so each anchor will get 1/6 of the applied tension, and the moment divided by this distance, which is 200 millimeters, gives us so this is the direction of the moment. Those anchors will be in tension, those anchors will be in compression. The tension will be the moment divided by this distance of 200 millimeters, and there are 3 bolts in the group, so that divided by 3. So each anchor on this side will be subject to a tension that is 1/6 of N sub UA, and this gives you 1/24 of N sub UA. 5/24 of the tension, the applied tension. And each of those anchors gets 1/8 of the applied tension. Okay, this is pretty simple stuff. I don't know that I need to dwell on it. The other eccentricity, the Y eccentricity, let me put everything on the screen. So that also causes the same moment, the axial load times the eccentricity. So that tension is equivalent to tension along the centroidal axis plus the moment. The tension along the centroidal axis is divided equally by the 6 anchors, and the moment causes additional tension on those 2 anchors and additional compression on those 2 anchors. The distance now is 300, so we divide the moment by 300, and now there are 2 anchors here, 2 anchors here, 2 anchors here. This is divided by 2. So this anchor gets a tension of 5/24 of the applied tension, and this anchor gets a tension of 1/8 of the applied tension. There is no compression here. This could go into compression, but that did not happen, either due to eccentricity or the Y eccentricity. So the maximum tension on an anchor, considering both eccentricities, comes out to 1/4 of the applied tension, and the minimum tension comes out to 1/12 of the applied tension, no compression. So we have checked and made sure that none of the anchors in the group is subject to net compression. So we are okay. We don't have to exclude any of the anchors. Okay, so we have 4 failure modes. First one is the anchor itself failing, just like a reinforcing bar fails under tension. So if that is our failure mode, the corresponding strength, this is nominal strength, is the number of anchors in the group times the effective area of the anchor in tension. This is the area of the anchor excluding the threads, and the ultimate tensile strength. The ultimate tensile strength of the anchor, in our case, I think it was 400 megapascal, I don't remember, has to be less than or equal to 1.9 times the yield strength of the anchor, which is 250 MPa. And it also, the ultimate tensile strength has to be smaller than 860 MPa. The effective area can be calculated using this formula, but there are design aids available, at least in the US, or I suppose that your anchor manufacturer will give you that effective area number. Okay. In our case, for the half-inch diameter anchors, the effective area is 79.35 square millimeters. The ultimate tensile strength, as I give you the right number, 400 MPa. That is in fact less than 1.9 times the 250, which is 475. It is also less than 860 MPa. So we satisfy the requirements that are imposed. The anchor, the tensile strength of a single anchor then is the area 79.35, the effective area of the anchor, multiplied by the ultimate tensile strength, and that is 31.74 kilonewtons. Okay? This is the nominal tensile strength of a single anchor in tension. Strength reduction factor, if you go to K.4.4, is 0.75 for ductile steel elements under tension. So this is still failure, so we don't have an additional 0.75 reduction. So the 31.74 kilonewtons of nominal tensile strength is reduced to 23.81 kilonewtons of design tension strength, P times N sub SA. This is still for a single anchor. Okay. Now, remember the maximum tension that any anchor in the group of 6 was subject to is 1/4 of the tension applied to the group. Okay? So if a single anchor can carry 23.81 kilonewtons, then the group can carry 23.81 multiplied by 4 or 95.24 kilonewtons. Okay, so please follow this closely. This is important. So a single anchor has a design strength of 23.81 kilonewtons. That is the maximum demand that can be put on a single anchor. Now, the anchor in the group that sees the highest tension experiences 1/4 of the tension applied to the group. So if a single anchor can be subject to 23.81 kilonewtons, the group can be subject to a design tension strength of 4 times 23.81, which is 95.24. This is the maximum tension demand that the whole board formation can support for steel failure in tension, 95.24 kilonewtons. Second failure mode, concrete breakout. This is what it looks like. The anchor, when it comes out, takes a truncated pyramid with it, failure angle 35 degrees. Obviously, if the anchors are close to each other, then those failure surfaces will interfere. And then we have a group of anchors rather than 2 single anchors. Okay, so if these 2 anchors were closer together, we would have a group of 2 anchors. The picture shows 2 isolated anchors subject to tension. Definition of breakout strength: the strength corresponding to a volume of concrete surrounding the anchor or group of anchors separating from the member. Now, this is the expression for concrete breakout strength in tension. Okay. Capital N is always tensile strength. CB is for concrete breakout. And this is a nominal strength that we have to reduce by a phi factor and an additional 0.75 factor because we have seismic design category C. Okay. The right-hand side looks pretty formidable, but let me go through each term at a time. This is everything here is important, and this is why I'm using numbers, because I show you the formula doesn't mean anything until you see numbers. A sub NC 0, the C for concrete. And when I speak, I won't use the C. Makes it easier for me. And to start with, the C wasn't there. So anyhow, so A sub N 0. A sub N, please listen to me closely every step of the way. A sub N is the projected area of the failure surface of a group of anchors. No, I didn't say it right. A sub N is the projected area of the failure surface of a single anchor or a group of anchors in tension. not considering spacing or edge distance. I'll repeat. A sub n is the projected area of the failure surface of a single anchor or a group of anchors in tension, not considering spacing of the anchors or edge distance. A sub n0, the quantity in the denominator, is the projected area of the failure surface of a single anchor in tension, now considering spacing between the anchors and the edge distance. Okay. The psi sub ED is a correction factor for edge distance. Psi sub C is a correction factor for possible absence of cracking. Remember, the basic equation is for cracked concrete. Psi sub CP is a correction factor for post-install anchors. And N sub B is a basic single anchor breakout strength. N sub B is a basic single anchor breakout strength. So remember, we have a basic strength for a single anchor in tension, in this case breakout, and then a set of correction factors to account for various things. The next formula is for concrete breakout strength of a group of anchors. So previous slide, we were talking about a single anchor. A sub n was for a single anchor. In this second case, it is a group of anchors. So A sub n now is the projected area of the failure surface of a group of anchors in tension, not considering spacing or edge distance. Now, in addition to the correction factors you saw on the previous slide, there is an additional correction factor which is for eccentricity of load application. Psi sub EC, this comma n means it is for tension. Okay, so accounts for eccentricity. Okay, let's talk about the definition of anchor group. A number of anchors of approximately equal effective embedment depth, each anchor spaced at least 3 times the embedment depth from one or more adjacent anchors when subjected to tension. Only those anchors susceptible to the particular failure mode under investigation shall be included in the group. That part I think is understandable upon reading. So a group is defined by a spacing less than 3 times the embedment depth. Now, we have 6 anchors. So we have 4 possibilities. We may have 6 isolated anchors, 2 groups of 3, 3 groups of 2 anchors each, or a group of 6 anchors. It will depend upon the spacing in each direction. In our X direction, the spacing is 200 millimeters, which is less than 3 times the effective depth of 300 millimeters. And in the Y direction, we have a spacing of 150 millimeters, which is less than 3 times the effective depth of 200 millimeters, 300 millimeters. So both ways, the spacings are close, and that means that we have a group of 6 anchors, not 6 isolated anchors, nor 3 groups of 2 or 2 groups of 3. We have a group of 6 anchors. Now, another complication. Where 3 or more edge distances are less than 1.5 times the effective depth, we use a reduced effective depth in breakout strength computations, where three or more edge distances for an anchor subject to tension are less than 1.5 times the embedment depth, we have to do our breakout strength calculations using a reduced effective embedment depth. Okay? And that reduced depth shall be equal to the larger of the maximum edge distance divided by 1.5 or the maximum spacing between anchors divided by 3. Okay, let's take a look. This is an example. We have an anchor. Edge distances are 100 millimeters this way, 100 millimeters that way, 100 millimeters this way. The effective depth is 200 millimeters. 1.5 times effective depth is 300 millimeters. So each of those edge distances is short. So we have an anchor close to 3 edges. Okay. So now we have to do the calculation with an effective embedment depth smaller than 200 millimeters. That effective embedment depth is going to be the largest edge distance. We have 3 edge distances that are all equal. So the largest is 100 millimeters divided by 1.5, which is 66 2/3 of a millimeter. So instead of the effective depth we actually have of 200 millimeters, we have to do our breakout strength calculations using an effective embedment depth of 66 2/3 of a millimeter. In this case, we have a single anchor, so there is no question of spacing. Next picture, we have a group of 2 anchors spaced at 225 millimeters. Edge distances are 150, 100, and 125. Largest edge distance is 150. That divided by 1.5 is 100. And the spacing of 225 divided by 3 is 75. The larger of those, which is 100 millimeters, is the effective embedment depth, whereas the actual embedment depth is 140 millimeters. Okay, so hopefully you got it. Okay, so in the example problem, the number of edge distances that are less than 1.5 times embedment depth, we have an embedment depth of 300 millimeters. 1.5 times that is 450 millimeters. We have 2 edge distances that are 100 millimeters. So our anchor group is close to 2 edges, not close to 3 or more edges. So we do not have to modify our embedment depth of 300 millimeters. Okay, A sub n0 and A sub n. Okay, so A sub n0 first. We have an anchor subject to tension. This is the anchor in elevation. This is the anchor in plane. If the failure angle is 35 degrees, then this distance is 1.5 embedment depth. This distance is 1.5 embedment depth, and it is the same into and out of the screen. Okay, that distance is 1.5. That distance is 1.5 embedment depth. So the projected area of the failure surface of a single anchor in tension, considering edge distance, the projected area of the failure surface of a single anchor in tension, not considering the edge distance or spacing, is 3 times embedment depth multiplied by 3 times embedment depth, which is 9 times embedment depth squared. In our case, 810,000 square millimeters. Okay, very simple. This has nothing to do with edge distance or spacing. This is for a single anchor in tension. A sub n0 depends only on the embedment depth. Then A sub n effective area, not effective area, the projected area of the failure surface by group of anchors in tension. Now considering spacing and edge distance. Okay, so this is an example. We have a group of 4 anchors. Edge distance this way is C sub 1. Edge distance the other way is, we have a large edge distance, but we cannot go any more than 1.5 times the effective depth. Okay. So that's the idea. 135 degree, not 135 degree failure cone means that this distance is 1.5 times embedment depth. If we have an edge distance shorter than 1.5 embedment depth, we have to go with the shorter edge distance. Spacing this way is S sub 1. Similarly, the other way, the spacing is S sub 2. This edge distance is 1.5 embedment depth because we have all kinds of concrete this way, but this edge distance is C sub 2. And so for an anchor or an anchor group subject to tension, C sub 1 is the shorter edge distance, C sub 2 is the larger edge distance. This is how our notation is. Okay. The A sub n in this particular case would be the C sub 1 plus S sub 1 plus 1.5 times embedment depth multiplied by 1.5 times embedment depth plus S sub 2 plus C sub 2. In our case, so we have a group of 6 anchors here. These distances we know 150, 150, edge distance 100. This way, the edge distance would be 1.5 times our embedment depth, which is 450 millimeters, because we have plenty of concrete this way. Along the x direction, edge distance of 100, spacing of 200, we have all kinds of concrete to the left, so we take 1.5 times the embedment depth, which is 450 millimeters. So our A sub n is the 450 plus 200 plus 100, which is this, multiplied by 100 plus 2 times 150 plus 450. And all of that gives us 637,500 square millimeters. A sub n cannot be any larger than n times A sub n 0, and we satisfy that requirement. The basic breakout strength is given by this expression where K sub C is 10 for cast in place anchors. Notice this is embedment depth raised to the power 1.5. There is an alternative equation where we can increase the power from 1.5 to 5/3, but the constant goes down from 10 to 3.9. So both are, so this is the general equation. If the embedment depth is between 280 and 635 millimeters, we have this alternative equation, and whichever equation, when both apply, whichever equation gives us the larger embedment depth, we are free to use. So by the first equation, the basic breakout strength comes out to 328.6 kilonewtons. By the second equation, which is applicable in our case because our embedment depth of 300 millimeters is between 280 and 635. By the second equation, we get a breakout strength of 338 kilonewtons. We are free to use the larger of the two. So our breakout strength is 338 kilonewtons. Eccentricity factor, we have an eccentricity of 25 millimeters each way. This is the correction, the expression for the correction factor, which cannot be any larger than 1. When we have biaxial eccentricity, we calculate two correction factors for the two eccentricities and take the product of the two as our eccentricity correction factor. The eccentricity is shown in this picture. We have three anchors subject to tension. In this group, it could be 6 or 9 anchors, whatever, you know. This is the resultant tension, and this is the centroidal axis of the anchor group. This is then the eccentricity. In this group of anchors, the left-hand anchors are subject to compression, so they don't count. So now the resultant tension acts along this axis. The centroidal axis of the anchor subject to tension is here. So this is the eccentricity that will have to be used in calculating our eccentricity correction factor. In our case, embedment depth of 300 millimeters, eccentricities of 25 millimeters each. If we plug in the numbers into the expression for the correction factor, we get 0.95 correction factor for each eccentricity. When we multiply the two, we have a correction factor for both eccentricities, which is 0.9. So 10% reduction in strength because of the eccentricities. The edge distance correction factor. If minimum edge distance is larger than or equal to 1.5 times the embedment depth, we have no correction for edge distance. If, however, the minimum edge distance is less than 1.5 embedment depth, then our correction factor is 70% plus 0.3 times the minimum edge distance divided by 1.5 times the embedment depth. So we have effective depth of 300 millimeters, minimum edge distance of 100 millimeters, which is less than 1.5 times the embedment depth. So our correction factor is 0.7 plus 0.3 times the minimum eccentricity of 100 divided by 1.5 times the embedment depth, which is 0.77. So because the anchor group is so close to the edge, 100 millimeters as opposed to 1.5 embedment depth, which is 450 millimeters, we lose 23% of strength. That's what it means. Cracking effect for uncracked concrete, which means the tensile strength under service load is less than the modulus of rupture. We get a correction factor of 1.25. If we have cracked concrete, the tensile strength, tensile stress under service loads larger than or equal to modulus of rupture, then the correction factor is equal to 1.0. Our concrete is cracked under service level loads. It was said in the problem statement. So we have a correction factor for cracking of 1.0. Okay, I said it before putting on the slide. Okay, so now we can calculate our breakout strength for the group of 6. A sub n, we calculate as 637,500. The A sub n, 810,000. Eccentricity correction 0.9, edge distance correction 7.7. The correction for possible absence of cracking 1. We have cast in place anchors, so post installed anchor correction is 1.0. Basic breakout strength 338 kilonewtons. So we have a group breakout strength of 184.35 kilonewtons. 3 factor. In this case of breakout in tension, there are 2 conditions that are set up. Condition A applies for concrete breakout and side face blowout when supplementary reinforcement is present. If there is no supplementary reinforcement, then for concrete breakout and side face blowout, And irrespective of supplementary reinforcement, when we are considering concrete pullout, it is condition B, which gives you a lower phi factor. Supplementary reinforcement definition: reinforcement that acts to restrain the potential concrete breakout, but is not designed to transfer the full design load from the anchors into the structural member. So it restrains potential concrete breakout, but does not suppress it. That's supplementary reinforcement as opposed to anchor reinforcement. Supplementary reinforcement is not specifically designed to transfer loads from the anchors into the structural member. Stirrups, as used for shear reinforcement, may fall into this category of supplementary, may act as supplementary reinforcement. In our case, we have taken a phi of 0.75, assuming that we have condition A, meaning we have supplementary reinforcement. We have seismic design category C, so we have an additional reduction factor of 0.75. So we have to reduce our nominal breakout strength by 0.75 multiplied by another 0.75. So we have to reduce it by 44%. Our combined reduction factor is 0.56. So 0.56 times the nominal concrete breakout strength for the group of 6 is 103.24 kilonewtons. Okay. If you have a plate washer on your anchor bolt, which some people use to enhance breakout strength, the advantage you get is if you didn't have the washer, your failure planes will start from here and there. If you have the washer, then your failure plane starts from here, where the distance this distance is equal to the thickness of the washer. The distance from the edge of the head to where you can draw your failure plane is equal to the thickness of the washer. So that may give you a somewhat larger projected area of the failure plane. That is the advantage you get out of a washer. It's typically not all that substantial, but every little bit helps. The concept of anchor reinforcement, where I should say something at this stage. I have 205 slides in the set. So I knew that there would be a huge time problem. I will go through the tension computations in its entirety, absolutely no question. Then I'll make my announcement, and then the shear part, we will go as far as we can. By then you will see that things are repetitive, and I don't think you will have any difficulty following this very explicit slide set that I put together. The slide set is complete, every number is spelled out, and so that is kind of the agenda. Okay, I anticipate running out of time. I do not anticipate there will be time for questions today, but I felt compelled. The Appendix K, if you try to use it, is pretty complex. So I felt obliged to make it as easy to use as possible, but the time that we have may not permit going through until the end of the slide set. We'll see. Okay. So where anchor reinforcement is developed, this part is very important. Where anchor reinforcement is developed in accordance with your section 8.3 on both sides of the breakout surface, developed on both sides, the design strength of the anchor reinforcement shall be permitted to be used instead of the concrete breakout strength in determining phi times n sub n. A strength reduction factor of 0.75 shall be used in the design of the anchor reinforcement. So supplementary reinforcement, I said, restrains breakout, does not suppress it. Anchor reinforcement suppresses breakout failure. So you don't have to calculate breakout failure strength. That is replaced by the design strength of the anchor reinforcement. Okay, A sub S times F sub Y of the anchor reinforcement reduced by a phi factor which is given as 0.75. So where anchor reinforcement, that is the key, is developed in accordance with 8.3 on both sides of the breakout surface, the design strength of the anchor reinforcement shall be permitted to be used instead of the concrete breakout strength in determining phi times m sub n. Okay. So anchor reinforcement. Reinforcement, this is definition, used to transfer the full design load from the anchors into the structural member. Okay. So the if you read between the lines, this is reinforcement that suppresses breakout failure. So this is very common anchor reinforcement in tension. So we have a group of 4 anchors. You see two, the other 2 are into the screen. Okay. There is a stirrup or whatever you want to call it in front. There is one at the back. Okay. So this piece of reinforcement is developed on this side. This is the failure plane. Okay. This is the shaded part, shaded area of concrete is what breaks out. On this side of the failure plane, we have L sub D, the required development length. On the other side of the failure plane, we have L sub DH, hooked bar development length, because this bar is hooked because of this, it is continuous into, okay. So this way it is straight bar development length, this way it is hooked bar development length. The other stipulation is that this distance between the anchor axis and the axis of the anchor reinforcement shall not exceed 1/2 of the embedment depth. Okay. Now this is the so that was the front view that I showed you. This is the side view. Okay, the same group of anchors. Same group of anchors. This is the front stirrup. This is the back stirrup. We are looking at the same group. Now, we didn't run any numbers with anchor reinforcement, but I did want to show you the very powerful concept of anchor reinforcement. The last tensile failure mode is pull-out. That is the anchor pulling out clean. No chunk of concrete coming with the anchor. Okay, that does not happen to headed bolts or studs typically. It does happen to hooked bolts because the hooks under large tension can straighten out, and then the anchor just pulls out. The pull-out strength, nominal pull-out strength, is a basic pull-out strength multiplied by a factor, size sub C for concrete, P for pull-out. If it is headed stud or bolt, headed stud or headed bolt, the basic pull-out strength is 8 times the bearing area of the head of the anchor multiplied by F sub C prime. So I want you to ponder this. So far everything was square root of f sub c prime because we were talking about tension. Here this is compression, 8 times f sub c prime. So the anchor is bearing on the concrete. The anchor head is bearing on the concrete, and it will take that much of force to have the anchor pull out of the concrete, 8 times f sub c prime times the bearing area. If it is a J bolt or an L bolt, the bearing area is E sub h times d sub a, the anchor diameter, multiplied by, I think I have a picture. So this would be E sub h. So bearing area would be E sub h times the diameter of the bolt. If it is a headed anchor, then the bearing area is the shaded area in the picture. Okay. If it is a headed bolt or stud, then the bearing area is multiplied by 8 times f sub c prime. That is the basic pull-out strength. But if it is a hooked bolt, bearing area is E sub h d sub a, as we saw, but we get a bearing strength of only 90% of f sub c prime. This is 8, this is 0.9. So just this is important because within ACI 318 the initial proposal was, let us not allow hooked bolts in seismic applications because they pull out. ACI 318 took the position that instead of a outright ban, we will assign a very small strength to the hooked bolts. So that will make it very, very difficult to design hooked bolts for seismic applications. Okay, this is not prohibition, but making it difficult to use. Okay, for uncracked concrete, the size of CP is 1.4. For cracked concrete, size of CP is 1.0. So coming to our example problem, 12 millimeter cast in place headed bolts with hexagonal head. That's what we have. Bearing area, this year manufacturer will give you 187.74 square millimeters. So basic pull-out strength is 8 times F sub C prime of 40 MPa times the bearing area, that is 60 kilonewtons. For concrete cracked under service load, which is what we have, the correction factor is 1.0. So we have a pull-out strength for a single anchor of 60 kilonewtons. This is for a single anchor. The P factor for pull-out strength, this is condition B automatically, is 0.7. We have a 0.75 reduction because this is design category C. So our total reduction is 53%, 0.53. So the calculated 60 kilonewtons goes down to 31.8 kilonewtons of design pull-out strength of a single anchor. Now remember, in our group of 6 anchors, the anchor that is subject to the largest tension is subject to 1/4 of the tension that is applied to the group. So if a single anchor can carry 31.8 kilonewtons, the group can carry 4 times 31.8 or 127.2 kilonewtons before the group pulls out. Okay, so the group pull-out strength is 127. So this is the maximum tension demand that the whole bolt formation can support for pull-out failure in tension. Final failure mode, side phase blowout. This is a not an easy one. So the picture tells you the whole story. These are headed balls or studs, fairly deep embedment, close to the side face. The cover is thin. So this is the definition. The strength of anchors with deep embedment but thin side cover corresponding to concrete spalling on the side face around the embedded head, while no major breakout occurs near the top concrete surface. Okay, the picture said it all. In determining nominal side face blowout strength for multiple headed anchors, only those anchors close to an edge, and close means embedment depth or C sub A1, the minimum, the shorter edge distance will be will be smaller than 40% of the embedment depth. C sub A1 smaller than 40% of the embedment depth. That's what close means. Only those anchors close to an edge that are loaded in tension should be considered. Their strength should be compared to the portion of the tensile load applied to those anchors. You will see, we have numbers. So single-headed anchor with deep embedment close to the edge, the side face blowout strength N sub SB is given by this expression. We know all the terms in there by now. If perpendicular edge distance C sub A2 is less than 3 times C sub A1, then this has to be modified by a correction factor that would be less than that is by this correction factor. Now so that was for a single anchor, single-headed anchor with deep embedment. For multiple-headed anchors with deep embedment close to edge, and anchor spacing less than, so close to edge and anchor spacing less than 6 times the shorter edge distance, the group strength is the single anchor strength multiplied by this expression. This is the spacing between anchors and C sub A1, you know. S is the spacing of outer anchors along edge. These outer anchors is very significant, as you will see when I show you the numbers. So in our example problem, anchors used are headed balls. Minimum edge distance we have is 100 millimeters, which is less than 40% of 300 millimeters, which is 120 millimeters. So in the X direction, we have an edge distance shorter than 40 millimeters. In the Y direction, we also have an edge distance shorter than 40 times the embedment depth. So we have side face blowout failure possible in both X and Y directions. The breakout strength needs to be calculated in both directions, and the smaller strength would govern. This is very important. Okay. So this is our anchor group. We are first considering side face blowout of those 3 anchors to the right. So these are the bolts under consideration. C sub A1 is 100 millimeters. Anchor spacing is 150 millimeters. So this is the 150 millimeters is less than 6 times the edge distance. So that condition is satisfied. The spacing between outer anchors is 300 millimeters. This is very, very important. S is not 150 millimeters. You remember, S is the spacing between outer anchors, and that in our case is 300 millimeters. Bearing area we saw earlier, 187.74 square millimeters, F sub C prime 40 megapascal. So the side face blowout strength of our group of anchors is 1 plus S of 300 between outer anchors divided by 6 times C sub A1 of 100 millimeters. 13 times C sub A1 of 100 millimeters, square root of A sub BRG of 187.74, lambda of one lightweight concrete factor, we have normal weight concrete, square root of 40 megapascal is 169 kilonewtons. This is the side face blowout strength of the group of 3 bolts to the right. Okay. And this is the nominal strength. The phi factor, assuming condition A, that we have supplementary reinforcement, is 0.75. And we have an additional 0.75 because we have design category C application. So the combined reduction factor is 0.56. So our 169 kilonewtons of side face blowout strength goes down to 94.64 kilonewtons. Now this group of 3 bolts to the right is subject to 5/8 of the tension applied to the group. Okay, this is very easy to follow, and we have gone through that at the beginning. So the group of 3 to the right is subject to 5/8 of the tension applied to the group. So if the 3 anchors to the right can carry 94.64 kilonewtons, the group will be able to carry 8/5 of that, which is 151.42 kilonewtons. That is the side face blowout strength of the group, the maximum tension demand that the whole bolt formation can support in side face blowout. That is very precise language that we used here. Okay. Then the 2 anchors at the bottom. Now this page I discovered actually this morning our time, not too long ago, was messed up. The red circle in your handout is here. It should be here. Please correct that. We are considering those 2 anchors. Those are the ones that will break out, not the middle ones. Also, these dimensions were in inches, and I have corrected both. So now the red is in the right place, and those distances are in millimeters. Okay, so please correct your slide, make a notation, and I'm really sorry that it happened and I didn't see it until, as I said, maybe 2 hours ago. Okay, so we are considering the side face blowout of the 2 anchors to the bottom. Minimum edge distance 100 millimeters, anchor spacing 200 millimeters, which is less than 6 times 100, so that condition is met. The spacing of outer anchors in the group, in this case, there are only 2 anchors, so the spacing is 200 millimeters. Bearing area remains unchanged, and F sub C prime remains unchanged. So the breakout strength of the group of 2, if you plug in the numbers that we know by now, is 150.21 kilonewtons. The phi and 0.75 for design category C brings the 150.21 down to 84.12 kilonewtons. The group of 2 anchors is subject to a maximum tension of 5/12 of the tension applied to the group. So the maximum tension demand that the whole bolt formation can support in side face blowout is 12/5 of the 84.12, which is 202 kilonewtons. So governing side face blowout strength of the whole bolt formation is the smaller of those computed by considering failure in X direction, the 3 bolts to the right, which was 151.42 kilonewtons, and the 2 anchors to the bottom, the Y direction blowout. And that gave us 202 kilonewtons, the smaller one corresponding to the 3 bolts to the right breaking out is 151.42. So finally we come to the bottom line. We have a steel failure strength of 95.24 kilonewtons. We calculated all these numbers. Concrete breakout strength 103.24. Pull-out strength 127.2. Concrete side face blowout, we just calculated 151.42. So the group strength in tension is the smallest of the 4, which is 95.24 kilonewtons, and it is governed by steel strength. So this group of anchors is suitable for application in buildings assigned to design category C or higher. Okay. Remember, design category C and higher, we cannot have concrete failure mode. So just to calculate the tensile strength of the group of 6 anchors, you saw the amount of trouble that we had to go through. Okay. And shear is still to come. But at this point, I would like to make an announcement which I think is quite important. I made an announcement earlier that we were mailing out a questionnaire that asks you about your experience with and perceptions of the P-Eng application process of BPERB and the requirements that you have to satisfy to write the P-Eng exam. At that point, we wanted only RAJUK enlisted engineers to complete our survey. We will resend that survey later today. Well, your time, it may be tomorrow morning, I don't know. Anyway, we will resend that survey to all of you. And please, we got quite a few replies, and thank you very much for that, but we would like more. So if you have not returned that survey, please fill it up and return it to us. It is electronic submission. It will not take you more than 10 minutes or so is my estimate. And this time, very importantly, we will open it up to everybody. You don't have to be a RAJUK enlisted engineer to return that survey. We have added a box that allows you to indicate that you are not enlisted by RAJUK. Fill up that box so that we know that you are not enlisted, but we want your views as well. What you think of the P-Eng requirements. Okay, with that, I will go to the shear part of the presentation. In tension, we had 4 failure modes. Now we have 3 failure modes. The anchor itself failing in shear, concrete breakout strength similar to breakout in tension, and then concrete pry out strength. We don't have side face blowout or pull out, but this pry out is like side face blowout. If we have a shallow anchor and it is subject to shear, it may kick out and damage the thin concrete at the top. I'll show you a picture when the time comes. Okay, our group of 6 anchors we are subjecting it to shear in both directions, X and Y. The X shear is concentric, but the Y shear is at an eccentricity of 25 millimeters. Okay, one shear is concentric, the other is eccentric. So as in the other direction, we will check whether so that the shear is to the right, and we will have to check if any of the anchors in the group were under concentric compression. That wouldn't happen, but this eccentric shear will cause a torsion, and because of that torsion, one or more bolts can develop a shear that is in a direction opposite to that of the applied shear, and those bolts have to be excluded from calculation. This is like you subject the group of anchors to tension, one of the bolts goes into compression, you have to exclude it. Yeah. So so similar computation as the last time, we have a shear applied at an eccentricity of 25 millimeters that is equivalent to a concentric shear plus a torsion. The torsion will cause additional shear in the anchors to the right. It will take away from shear from the anchors to the left. Now this take away should not reverse the direction. So that's what we are checking. Maximum shear comes out to 5/24, minimum shear is 1/8. There is no shear reversal. Okay, so that is like checking for an anchor going into compression. The steel failure mode, shear, the anchor itself failing in shear. This is what the failure mode looks like. This picture, although hand-drawn sketch, is pretty descriptive. This is not very different from the tensile failure, although I think this part of the picture is very descriptive of what is happening. Yeah. So shear failure of the anchor itself. If we have, this is important, if we have cast in place headed starred anchors, these are headed studs only, not bolts, okay, then the steel strength, the shear strength of the, how should I say, the steel governed shear strength of the anchor is number of anchors in the group, the effective area of the anchor in shear, this is excluding the area of the threads, and the ultimate tensile strength. This is the same as the shear strength is the same as the tensile strength, no reduction. Cast in place headed studs only, we have no reduction. Everything else, cast in place headed bolts, hooked bolts, we have 60% of F sub UTA multiplying the number of bolts, number of anchors, and the effective area of an anchor in shear. Okay? 60% reduction. So you would, I think, expect a reduction, but based on testing and observations for headed studs, there is no reduction in. So we multiply by full F sub UTA, not without a reduction. Okay, so I want you to pay attention to that. If we have built up grout pads, which are not uncommon, we reduce the anchor strength by 20%. This is very rough. There is quite a bit of literature on that subject. It's a complex subject, but anyway, that's what 318 has decided to do. As before, F sub UTA, the ultimate tensile strength of the reinforcement cannot be any larger than 1.990% of the yield strength, nor any larger than 860 megapascals. The effective area in shear can be calculated from that expression. Your best bet is to get that area from the manufacturer. In the example problem, our effective area is the same as in tension, 79.35 square millimeters. The ultimate tensile strength of the anchor 400 MPa, which is less than 1.9 times 250, which is 475, also less than 860 MPa. So our steel governed shear strength is 60%. We have headed bolts, not studs. So 60% of the 400 MPa multiplying the 79.35 square millimeters for a single anchor is 19 kilonewtons. Okay, 19 kilonewtons. This is nominal value. Phi factor for shear failure of steel anchor is 0.65. Ductile steel element under shear 0.65. No additional 0.75 because this is a steel failure mode, not a concrete failure mode. So the design shear strength is 19 times 0.65, which is 12.35 kilonewtons. This is for a single anchor, single bolt. Now, for shear in y direction, where we have an eccentricity, equating the, so in the y direction, for y direction shear, maybe it is worth going back. For y direction shear, the anchor that experiences the most shear experiences 5, 8, what's the number? I'm sorry, I skipped the number. 5/24ths of the shear applied to the group. Okay, so the maximum shear on a single anchor is 5/24ths of the anchor applied to a group. So we have a single anchor strength of 12.35 kilonewtons. We have to multiply that by 24/5 to find the maximum shear demand that the whole bolt formation can support for steel failure in shear. Okay, 24/5 times the calculated 12.35, that comes to 59.28 kilonewtons. Shear in X direction, where we have no eccentricity, each anchor experiences 1/6 of the shear applied to the group. So the group strength is 6 times the calculated 12.35, which is 74.1 kilonewtons. So this is X direction shear strength. The other number is Y direction shear strength, 74 versus 59.28. And the reduction from 74 to 59.28 is because of the 1-inch eccentricity of the shear in the Y direction. Concrete breakout in shear. This is what it looks like. Okay. This is the chunk of concrete that breaks out for shear in the left to right direction. The equation, similar to the equation for tension, we are talking about here the breakout strength of a single anchor in shear. A sub B is then the projected area of the failure surface of a single anchor in shear, considering spacing and edge distance. A sub B0 is the projected area of the failure surface of a single anchor in shear, now not considering edge distance or spacing. This is correction factor for edge distance. This is correction factor for absence of cracking. This is correction factor for insufficient depth of concrete. This is different in for this correction factor. We didn't have in tension, but in shear, this is a correction factor for possibly insufficient depth of concrete, and you will see what it is. And then a basic single anchor breakout strength in shear. On the next slide, it is breakout shear strength, shear breakout strength of a group of anchors. So A sub B now is the projected area of the failure surface of a group of anchors in shear, considering spacing between anchors and edge distance. A sub B0 is the projected area of the failure surface of a single anchor in shear, not considering edge effect or spacing. When it is a group, we have an additional correction factor for eccentricity of load application, eccentricity of shear application. Okay, we looked at the definition of an anchor group in tension. Now, what is the definition of an anchor group in shear? A number of anchors of approximately equal effective embedment depth, with each anchor spaced at less than 3 times C sub A1. Now, a couple of very important things. When we were talking about tension, C sub A1 was the shorter edge distance, C sub A2 was the larger edge distance. When we are talking about anchor subject to shear, C sub A1 always by definition is edge distance in the direction of shear. C sub A1 is in the direction of shear. C sub A2 is perpendicular to the direction of shear. This is very, very important. The other important thing is the role played by H sub EF, effective embedment depth. The role that effective embedment depth plays in tension is played by C sub A1, the edge distance in the direction of shear when it comes to shear failure modes. Okay, so you pretty much have to replace wherever you used H sub EF in the tension strength equations by C sub A1 in shear strength equations. I hope what I'm trying to say is clear. Okay, so a group meant distance between anchors less than 3 times embedment depth when it was tension. Now a group means spacing between anchors less than 3 times C sub A1 when we are talking about anchors in shear. Okay, so do we have 6 isolated anchors, 2 groups of 3, 3 groups of 2, or a group of 6? For X direction shear, the edge distance in the direction of shear is 100 millimeters, which is less than the so we have an edge distance in the direction of shear of 100 millimeters. 3 times 100 millimeters is 300 millimeters. The spacing in the x direction is 150 millimeters. So we have a spacing less than 3 times C sub A1. In the y direction, C sub A1 is 100 millimeters, 3 times that is 300. We have a spacing of 200 in the y direction. So 200 is also less than 300. So both distances, both spacings being less, we have a group of 6 anchors. Okay. In the x direction, we have a spacing less than 3 times C sub A1. In the y direction also we have a spacing less than 3 times C sub A1. So we have a group of 6 rather than 6 individual anchors or 2 groups of 3 or 3 groups of 2. Now, how do we, so everything in Appendix D or your Appendix K is shear perpendicular to the edge. How do we calculate shear strength parallel to the edge? So this is what you do. You compute, you need to compute shear strength parallel to this edge. What you do is compute shear strength perpendicular to the same edge, which we know how to do. That's what Appendix K tells us. And then based on testing, shear strength parallel to the edge would be just 2 times the perpendicular to the edge value, 2 times V sub n. If shear strength perpendicular to the edge is V sub n, shear strength parallel to the same edge is simply 2 times V sub n. This is crude, but this is what we have in Appendix D of 318. Even now, 3 and ACI 319 has the same thing, and in Appendix K you have the same thing. For shear force parallel to the edge, B sub CB, breakout strength would be 2 times breakout strength that is perpendicular to the edge, and group breakout strength will also be 2 times the group breakout strength perpendicular to the edge. At the corner, if you have an anchor at the corner, use the smaller value of strength perpendicular to the edge and strength parallel to the edge. I think if you think about it, you will see that it makes a lot of sense. Okay, A sub B 0, okay, projected area of the failure surface of a single anchor in shear, not considering spacing or edge distance. So this is a single anchor in shear in plane. The failure surface is at 35 degrees, which will make this distance 1.5 C sub A1, that distance 1.5 C sub A1. This is the same anchor in elevation. Okay, this is 1.5 C sub A1, this distance. This is 1.5 C sub A1, that distance. This is the anchor in elevation, side elevation. Okay, this is the chunk of concrete that breaks out in shear. If the failure angle is 35 degrees, then this depth is also 1.5 times C sub A1. Okay, so this is what breaks out on the surface, on this face. Okay, the extent of the breakout this way is 3 times C sub A1, and the depth of that breakout is 1.5 times C sub A1. So A sub B0 is, sorry, something. something, things pop up. Okay. So this distance is 3 times C sub A1. This is 1.5 times C sub A1. So A sub B0 is 3 times C sub A1 times 1.5 C sub A1, which is 4.5 C sub A1 squared. Okay. It depends only on C sub A1 and on nothing else. Just like A sub N0 depended only on embedment depth and on nothing else. Now comes some well, it's not anyway. Follow me closely, as I hope you have been doing all along. So if the depth of concrete is less than 1.5 times C sub A1, and the spacing between anchors is less than 3 times C sub A1, here we are looking at a group of 2 anchors, and shear applied perpendicular to the group, the axis of the group of anchors. So what will break out on the surface is, this chunk of concrete will break out. I hope you are following my arrow. So this is the group of 2 anchors. This is the shear. And under that shear, if it is high enough, a chunk of concrete will break out that will look like this, that. Okay. So on the surface, what will break out is what we have shaded. This distance is S sub 1. This distance is 1.5 times C sub A1. This distance is 1.5 times C sub A1. And the depth is H sub A. So what is breaking out? A sub B is 2 times 1.5 C sub A1, this side and that side, plus S sub 1 times the H sub A. This is now also a group of 2 anchors, but the shear is now parallel to the group. Okay. The depth of concrete is less than 1.5 times C sub A1. First, we consider the possibility that the first anchor breaks out, and it breaks out under 1/2 the shear applied to the group. Okay, the shear applied to the group is shared equally between the two. So this anchor gets half the shear applied to the group, and it breaks out. The edge distance is C sub A1. So the distance that breaks out this way is 1.5 C sub A1, that way 1.5 C sub A1, and this is H sub A. So A sub B is 2 times 1.5 C sub A1 times the depth. The second possibility is the front anchor doesn't break out. The way the 2 anchors are connected by base plate or something, the front anchor begins to yield and transfer the loads to the back anchor. And the back anchor fails under the total shear applied to the group. Now the edge distance is C sub A1, this larger edge distance. So what breaks out is this 1.5 times the larger distance, 1.5 times the larger distance. So A sub B now is 2 times 1.5 the edge distance to the back anchor multiplied by the thickness of the concrete. The basic breakout strength of a single anchor in shear is given by this expression. This L sub E is the embedment depth for anchors with constant stiffness, but it cannot be taken any larger than 8 times the anchor diameter. Okay, So this L sub E is equal to the effective depth, but no larger than 8 times the anchor diameter. If so, okay, now this is the basic equation. 0.6, the L sub A over D sub A raised to the power 0.2, etc., etc. If you are able to satisfy 5 given conditions, and I will not go through them in view of our time situation, then there is an alternative equation that you are allowed to use. Now, in the basic equation, the constant was 0.6. In the alternative equation, the constant is 0.66. You get a 10% advantage. The rest of it is the same. So if you are able to satisfy the 5 conditions, then you are allowed to use the second equation. Just as in tension, we consider the possibility that our anchor may be close to 3 or more edges, we have to consider the same possibility here, but here close to an edge would mean edge distance less than or equal to 1.5 times C sub A1, not embedment depth. Okay, C sub A1 is again the edge distance in the direction of shear. So where 3 or more edge distances are less than or equal to 1.5 times C sub A1, then we will have to adjust instead of actual C sub A1, we will have to use a reduced effective C sub A1. Okay, and let me just go to the example, and I will tell you what it is supposed to be. Okay, so we have a group of 2 anchors. Edge distance this way 300 millimeters, this way 125. This is, so the edge distance in the direction of shear C sub A1 is 300 millimeters. Okay. The perpendicular edge distances are what we need to look at: 125, 180, and 200, the depth of the concrete. That is also an edge distance now. So we have an edge distance in the direction of shear of 300 millimeters, and we have 3 perpendicular edge distances of 125 millimeters, 180, 200. The spacing between anchors is 230. So the effective C sub A1 will be the largest of the edge distances, 125, 180, or 200. The largest is 200. 200 divided by 1.5, or 230 divided by 3, whichever is the larger of the two. Again, the effective C sub A1 that we have to use is the largest of the edge distances of 125, 180, or 200, which is 200 divided by 1.5. That's one number. Or the 230 divided by 3, that is the second number, larger of the two numbers. Effective C sub A1. Okay. Correction factor for eccentricity of shear given by this expression. The eccentricity is illustrated in this picture. This is the resultant shear. This is the centroidal axis of the group of 2. The correction factor for edge distance, if the perpendicular edge distance is larger than or equal to 1.5 times the edge distance in the direction of shear, no correction. If perpendicular edge distance is less than 1.5 times edge direction in the direction of shear, then the edge distance correction is 0.7 plus 0.3 divided by this expression. The Correction factor for uncracked concrete. This is now much more complicated. If it is uncracked, it is 1.4. If it is cracked, it is not automatically 1.0 as in the case of tension. Size of CV is 1.0 if there is no supplementary reinforcement, or there is supplementary reinforcement but it consists of bars that are less than number 13 in size. If you have supplementary reinforcement consisting of bars larger than or equal to number 13 in size, then the correction factor is 1.2. And if you have supplementary reinforcement consisting of bars that are larger than number 13 in size, and the supplementary reinforcement is enclosed within stirrups with a spacing not to exceed 100 millimeters, then you are as good as uncracked concrete. You get 1.4 correction factor. Okay, so illustration of what we were talking about. So shear cracked concrete. Well, yeah. So the first case is no supplementary reinforcement, or if you have supplementary reinforcement, it consists of bars thinner than number 13 in size. So no supplementary reinforcement, correction factor is 1.0, cracked concrete. Second picture, we have supplementary reinforcement supposedly consisting of bars larger than number 13 in size. Correction factor is 1.2. Third picture, we have supplementary reinforcement consisting of bars larger than number 13 in size, and they are enclosed within stirrups. So we have correction factor of 1.4, making this case as good as uncracked concrete. The correction factor for insufficient depth, if the concrete depth is less than 1.5 times C sub A1, then this is your correction factor given by this expression. So coming back to our example, this is Y direction shear where we have an eccentricity of 25 millimeters. From here on, it gets in a way complicated, but in a way repetitive. Okay, so please follow me closely on this first one, and then I will do a lot of skipping because it is all repetition. So the possibilities are those two anchors break out under 1/3 of the shear applied to the group. If that does not happen, those two anchors may break out under 2/3 of the shear applied to the group. Those two transfer their shear to those two. And if that does not happen, then the back anchors break out under the entire shear applied to the group. Yeah. So we are now considering the front anchors breaking out under 1/3 of the shear applied to the group. C sub A1 is 100 millimeters. Depth of concrete is 460 millimeters. That is larger than 1.5 times C sub A1. C sub A2 to the right is, so C sub A1 is 100. C sub A2 to the right is 100 millimeters. C sub A2 to the left, we are taking it as 500 millimeters. We have a lot of concrete to the left, but for calculation purposes, we are taking the edge distance as 500 millimeters. So we have only one edge distance that is less than 1.5 times C sub A1. So we do not have an anchor close to 3 edges. So C sub A1 of 100 millimeters does not have to be adjusted down. A sub BC, what breaks out on this surface? what breaks out is 1.5 times C sub A1 plus the spacing of 200 millimeters plus the 100 millimeters edge distance, and into the screen the depth is the smaller of either the depth that we actually have 60 or 1.5 times C sub A1. We cannot go any more than that. Okay. So 1.5 times 100 plus 200 plus 100 plus 1.5 times 100, H sub A is larger than that. So we get an A sub B of 67,500 square millimeters. This is calculated value. This is what breaks out on that surface. A sub B0 is 4.5 times C sub A1 squared, and that for 100 millimeters of C sub A1 is 45,000 square millimeters. Number of bolts involved is 2. There is a stipulation that A sub B cannot be any larger than n times A sub B0. That did not happen, so we are okay. So we are considering shear in the y direction. As you know, we are considering the front two anchors breaking out under 1/3 of the shear applied to the group. Basic concrete breakout strength given by this expression, L sub E, remember, is equal to the effective depth, but cannot be taken any larger than 8 times the anchor diameter. In our case, the anchor diameter is 12 millimeters, so 8 times 12 is 96. So the 96 governs. L sub E is 96 millimeters. So P sub C is 0.6. L sub E of 96 divided by D sub A of 12. Square root of D sub A of 12, lambda is 1, square root of 40, C sub A1 of 100 raised to the power 1.5. All of that gives us 20 kilonewtons of basic concrete breakout strength, 20 kilonewtons nominal value. Okay. So this is basic concrete breakout strength, B sub B. Eccentricity factor in our case, y direction shear, we have an eccentricity of 25 millimeters. That gives us a correction factor of 0.86 for an edge distance of 100 millimeters. The edge distance correction, C sub A2 to the right is 100 millimeters, which is less than 1.5 times C sub A1. So edge distance correction is 0.7 plus 0.3 times C sub A2 of 100, 1.5 times C sub A1 of 100. That gives us 0.9. That is edge distance correction. The cracking factor, assuming that we have supplementary reinforcement, our cracking factor comes to 1.2. Concrete depth factor, we have plenty of depth. 460 that we have is way larger than 1.5 C sub A1, so we don't have any correction for insufficient depth. So shear in y direction, the group breakout strength is the A sub B of 67,500 square millimeter calculated value divided by A sub B0 45,000 square millimeter calculated value, eccentricity correction 0.86, edge distance correction 0.9, cracking factor 1.2, correction for insufficient depth 1.0, basic breakout strength of 20, which is 27.86 kilonewton. Okay, so for the group of 2 to the front, breaking out in shear, the strength is 27.86 kilonewtons. This is nominal strength. Phi, we again have condition A, condition B. Assuming that we have condition A, P is 0.75. But because this is a concrete failure mode, we have another 0.75 reduction. So the total reduction is 44%. Our calculated value of 27.86 goes down to 15.6 kilonewtons. Now, this 15.6 kilonewtons is under 1/3 of the shear applied to the group. Remember, these are the front two. So the total shear demand that the whole group can support before mode 1 failure takes place, the front two breaking out, is 3 times the 15.60, which is 46.80 kilonewtons. Okay. Now we consider the possibility that the middle two break out under 2/3 of V sub U. So now the C sub A1 distance increases to 250 millimeters. Okay, so that's what changes. The C sub A1 changes from 100 to 250. All the calculations that I showed you are repeated for the second case, and the bottom line number is the V sub, so reduce the concrete breakout strength of the group of two in the middle, reduced by 0.75 and phi, comes to 34.93 kilonewtons. Remember, those middle two break out under 2/3 of the shear applied to the group. So the total shear demand that the whole group can support before mode 2 failure takes place, the middle two breaking out, is 1.5 times 34.93, which is 52.4 kilonewtons. Then we consider the third possibility, the back anchors failing under the total shear applied to the group. And that takes us to now very interestingly, I should point this out. So now the C sub A1 has increased to 400 millimeters. This group of two now become close to 3 edges because C sub A1 is so large. So the C sub A1 of 400 has to be adjusted down to, I don't remember the number, it came to 333.33 millimeters. Okay, so this very large edge distance of 400 millimeters meant that the anchor group, that group of two, is close to 3 edges, and because of that, the 400 millimeters of edge distance had to be adjusted down to 333.33 millimeters. So going through the same calculations that I have shown you twice now, the strength comes out to 45 kilonewtons. Okay. Now that is the total thing. And the back anchors were failing under the total shear applied to the group. So 45 kilonewtons is the number that the whole group can sustain. So for the first two anchors the front anchors breaking out, the group strength was 46.8 kilonewtons. For the middle two breaking out, 52.4 kilonewtons. For the back anchors breaking out, 45 kilonewtons. So the group breakout strength actually for Y direction shear is 45 kilonewtons. X direction shear, we have two possible failure modes. The three anchors to the right breaking out or the three anchors to the left breaking out. Okay. Skipping all the calculations, going to the bottom line, this is concentric shear, no eccentricity correction. So for the front three breaking out, it is 22.18 for the group, for the three, and because they are subject to because they are failing under 1/2 of the shear applied to the group strength is 44.36 kilonewtons. For the back, the left three breaking out under the total shear applied to the group, the strength comes to 90.35 nominal value reduced by 0.56, it comes to 50.6 kilonewtons. Okay. So the front to breaking out 44.36, back to breaking, not back to the front three breaking out 40, not front, the three to the right breaking out 40.36 kilonewtons. The three to the left breaking out 50.6 kilonewtons. So the breakout strength is 44.36 kilonewtons. Okay. So it's almost 11 your time. Our regulation time is running out. Anchor reinforcement in shear, a very important topic, but I will again, as for anchor reinforcement in tension, it has to be developed on both sides of the failure plane. This way, you have to have full L sub D. This way, the continuity itself provides that the fact that it goes around provides development. So you don't have to worry about this. So this kind of a hairpin is very popular shear anchor reinforcement or a spread hairpin like that. This is a group of two anchors. This is fully developed. This is very popular shear anchor reinforcement. Here we have a group of four anchors sitting close to an edge. This is the anchor reinforcement that is provided from under time pressure. I tend to do this. So let us go back. Let me slow down. I'll go over a little bit, obviously. If you have to go, you have to go. But let me at least finish this topic, and maybe I'll talk very briefly about ply-out failure, and then then we'll be done for the day. This is a lot of stuff. I knew that, but I had no, I mean, shortening it would not have been advisable. Okay, so group of two anchors. This is the hairpin used as shear reinforcement. If you look at this section, that's what the section looks like. Okay, this is the anchor, the hairpin that we were talking about. And under this shear, this is what breaks out. Okay, so this is trying to break out, and this anchor reinforcement is trying to suppress that breakout. This is the important picture. So it could be a hairpin or it could be a spread hairpin, and the key thing is that this has to be fully developed. Here we have a group of two anchors, shear perpendicular to the group. This is what wants to break out in plane. What we do here is run supplementary reinforcement along the edge, and then anchor reinforcement that is supported by the supplementary reinforcement at the edge. In section BB, this is section BB. If you cut a section here, the section shows you this is the supplementary reinforcement. This is the anchor reinforcement that is supported by the supplementary reinforcement. And this anchor reinforcement is trying to suppress this breakout, this kind of breakout that is shown by the shaded portion. Okay. So anchor reinforcement in shear, very, very important in applications, and that's as much as I'm able to show you. Pry out failure, I think this picture is very, very graphic. So this is a shallow anchor. It under shear, it kicks out and destroys the thin cover concrete to the top. The language describes the picture, so it is unnecessary to go into. So the pry out failure, single anchor shear strength corresponding to pry out failure is the breakout strength in tension. I want you to pay attention to this, times a constant. This constant is 1.0 for very shallow anchors, embedment depth less than 65 millimeters, and is equal to 2 when embedment depth is larger than 65 millimeters. So let me make a very important point so far. If you look at the other two failure modes in shear, the steel failing or concrete breakout, the embedment depth does not play any role. So is shear strength independent of embedment depth? Is shear strength totally dependent only on C sub A1? This failure mode tells you no, absolutely no, because N sub CB is a tensile strength. It is a function of embedment depth. Also, K sub CP, you see how important embedment depth is. If embedment is shallow, all you get is 1. Okay, so to get a value of 2 here, you have to have embedment more than 65 millimeters. So for very shallow embedment, you get penalized twice. This constant goes down to 1, and this number will be small. In our case, we have embedment depth far exceeding 65 millimeters, so we have a K of 2. The breakout strength in tension, if you go back many pages, was calculated at 184.35. So the pry out strength is 368.7 kilonewtons. Reduced by 0.75 and the P factor of 0.7. Now it is condition B by definition for pry out. So the P is 0.7. We get 53% of the nominal value, or 195.41 kilonewtons. Okay, so this is the bottom line. Steel failure strength 74.1 kilonewton for X direction shear, 59.28 for Y direction shear. Concrete breakout strength 44.36 for X, 45 for Y. Pry out, irrespective of direction, 195.41. So the group strength for shear in X direction is the smaller of the two values, 44.36, and the group strength for Y direction shear is the smaller of 59.28 and 45, which is 45. So the minimum, the strength in this case, the shear strength for both X shear and Y shear is concrete governed strength. So this group is not suitable for design category C application. Remember, you have to have steel failure, so you have to make some changes if you are going to, if not if, our design category is C, so we cannot use this group of anchors as presented to you. Okay. The shear tension application, we are out of time, so I will just tell you that we used to use this kind of an interaction equation. ACI 318 has replaced that by this three linear segment interaction. So as long as the applied tension is no more than 20% of the design tensile strength, that much of tension has no impact on shear strength. Shear strength doesn't decrease. But if the applied tension is larger than 20% of the design tensile strength, then shear strength decreases linearly as given by the middle portion in the picture. The final thing that I do want to mention is if you have a slab and the slab is subject to tension as shown in the picture, the failure will be by splitting cracks developing in the slab. So why isn't splitting failure a failure mode? That is because ACI 318 has decided to preclude splitting failure. At design stage, specific products may not be known. In absence of supplementary reinforcement for crack control, this section, K.8, sets minimum cover and minimum spacing and minimum member thickness requirements. Okay, so you have to have, so in other words, ACI 318 and Appendix K puts limitations on cover, spacing, and thickness in order to preclude splitting failure. So splitting failure is simply not allowed to take place. Final thing, at least until ACI 31808, which is BNBC 2020, we had these limitations. Now it's a somewhat of a different story, but I don't want to confuse you with later editions of ACI 318 because then we never end. So for anchors with diameters not exceeding 50 millimeters and tensile embedment not exceeding 635 millimeters, the concrete breakout strength requirement shall be considered, etc. The concrete breakout strength expressions that I showed you in tension and in shear, those expressions are good only as long as your anchor diameter does not exceed 50 millimeters and as long as tensile embedment depth does not exceed 635 millimeters. Okay, keep that in mind. Those are limitations coming out of Stuttgart tests. They, in Stuttgart, did extensive anchor tests, but they did not go beyond 50 millimeter diameter anchors and they did not go beyond 635 millimeter embedment depth. So it was felt safe to put those limitations on. Okay, and I did want to mention that to you. That brings us to an end of the long presentation. Hopefully the presentation you have benefited from, and more importantly, I think this slide set will do you a lot of good. If you have to design anchors using Appendix K, I hope that you will. I'm pretty certain that you will find this slide set to be of great value. We have spent a lot of time and effort on this. This is in metric in your units. Appendix K section number set here with rare exceptions where I missed. You have D point something section, just replace the D with the K and you will have your section number, your Appendix K section number. Okay, with that, I thank you very much for your attention, and please do not forget to fill up and return those surveys to us. Thank you very much. It's always a pleasure to talk to you, and I'll see you fairly soon, but not tomorrow. Okay, tomorrow we have no seminar. Tomorrow's seminar was postponed to a later date. I don't have the date. I cannot give it to you off the top of my head, but you got an announcement.
The 28th, Dr. Ghosh.
Say that again.
The 28th of June.
28th of June?
Yes.
Okay. Okay. So tomorrow's seminar has been postponed to June the 28th. Okay. Thank you so very much. I'll switch off.